Hello everyone. Today I am going to present my project Quantum Secure Check, which demonstrate how concepts from quantum cryptography can be integrated into a desktop application. The main object of this project is to secure exchange messages using key generated through quantum BB84 protocol, simulated using Qiskit. Once the key is generated, it is mainly used for encrypt and decrypt messages through a ZOR cipher. We are going to use ZOR gate also for the operations furthermore in this project. The project is developed using Python, Qiskit AI simulator and Tkinter. Why this project is important or why this project plays a role? Let us understand first. In traditional communication system, the biggest challenge is securing sharing of message. Like somewhere they are not encrypted between two parties, and the thief or the attacker can get access to the key. The encrypted messages cannot be compromised. Quantum key distribution solves this problem using principle of quantum mechanics to generate a shared secret key. Any attempt to observe or intercept quantum information can be make it really traceable at what point and who is disturbing the message. My project demonstrates this concept in simplified and practical way. The project structure is like we have three mainly files: the crypto.py, the GUI.py, the QKD.py. This is for quantum key distribution. The crypto key is for the securing, like whether the message is encrypted or decrypted once the key is generated, and GUI is basically just for the user interface what is shown to you. I will explain this project, and first of all let us go through the overall workflow. Okay, so the workflow can be divided into 4 stages. First stage is quantum key distribution, second is key shifting, third is message encryption, and fourth is message description. So quantum key generation, it is all about following the BB84 protocol. First, Alice generates random bits, random bases. Bob also like randomly select measurement bases. There are two types of measurement bases. So let us first understand about the GUI, the main file of this project. This is the main application of this project. It is responsible for creating graphical user interface, connecting all the components together which are used in this project. First, I import the Tkinter for building GUI and threading to prevent the interface from freezing during the key generation, and the functions from my QKD and cryptography modules. So then I also imported the QKD and crypto files which I have created so that I can just integrate them all in the main file. The quantum key generation logic is implemented in the QKD file, while the encryption and decryption logic are implemented in the logic file, which is crypto.py. So next I define that for different colors or the different fonts I have already mentioned, and I don't think that I have to go in much deeper for this GUI file because it is like not important for the time being. Like we just need to focus on the QKD and the crypto.py so that we can cover the maximum important part in the minimum time, right? So let us understand first about the QKD. So the file implements BB84 protocol, which is using the Qiskit, and the purpose of this module is to generate a shared secret key that will later be used for message encryption. The main function is generate quantum key. This length parameter which is there, it helps us to specify that how many qubits we are going to use in this simulation. First, I initialize air simulator so that actually I'm not using the real quantum computer, right? So air simulator allows me to simulate quantum circuits on a classical machine. After that, the Alice is there. Alice helps us to randomly generate bits and bases. So that's what we have done. We have generated the random bits and bases. Then we have taken the help of Bob, which helps us to randomly pick measurement bases, which can be either rectilinear or diagonal bases. After that, the Bob chooses each qubit for which I am creating a new quantum circuit. Getting my point? Like here you can see QC equal to quantum circuit 1, 1. So the circuit contains 1 qubit and 1 classical bit as mentioned here. To encode Alice bits I apply X gate, and to encode Alice bases I applied Hadamard gate, which is QC.H. H stands for Hadamard gate. After that it changes the qubit from 0 to 1. The Hadamard gate places into the diagonal bases. The diagonal bases were the plus sign or the multiplication sign, which is mentioned above. Right? So after that qubit is measured, the QC measure comes out to be 0, 0. Then the circuit is executed on the simulator. Okay, and it results us to compile the sorts. Sorts mean how many times we are running the whole simulation. So measurement is done, simulation is done. Now the box measures a bit. Okay, the most important part is the key shifting. If Alice basis is equal to Bob basis, means the I of Alice basis is equal to the I of Bob basis. Only when Alice and Bob use the same basis to do, they keep the measured bit. If bases are different, the bit is discarded. This follows the actual BB84 protocol. All matching bits are collected into a list called key. Finally, shifted bits are combined into binary string and returned. The binary string becomes very secret quantum key used for encryption module. And in the crypto key, we have two functions mainly. The function which we are using for the encryption and the function which we are using for the decryption. So it is the most easiest part. Like decrypt button is pressed, the function is executed, it retrieves the ciphertext in the calls. The original message is then recovered and displayed in the decrypted section. Finally, I added status message and error handling throughout the application. For example, if the user attempts to encrypt without generating a key, an error message is shown instead of allowing the operation to proceed. And if we talk about for encryption, the file is encrypted, the text basically, when the encrypt button is clicked. The first, it checks whether a key exists or not. This ensures that encryption cannot be occurred without quantum generated key. The message entered by the user is then passed to the encryption module. Then returned, the ciphertext is displayed in the encrypted section. So overall, this file acts as a controller of the project. It provides a user interface and coordinates communication between the BB84 protocol key, which are we using for the generation of module, and the zone-based encryption module. Okay, so let me just so here is my project, quantum secure check. Let us type a message. Hi viewers. Okay, that would be fine. And first of all, we have to create a key for it. Let's generate key. The key is generated. Here are the bits, quantum key, which is 12 bits. It is fair, kind enough. And the strength is also, so I have mentioned about it. And let's encrypt it. The encrypted text, the message is this. And after encryption, here it is also showing that 11 characters were there and 11 to 11 it is encrypted. After that, we will decrypt. So the message which is transferred from one person to another person, one place to another, this message is being transferred. If anyone interrupt or disturb the communication, he or she will be getting the encrypted message, not the actual message. And once the message is encrypted and delivered and again decrypted, at the base station they are going to get the correct message or the message which we have started from the initial stage. So quantum key really plays a very crucial role in encrypting and decrypting the message. It is really a good score for the safety and secure communication. So okay, I will just in a nutshell, if we talk about this project, demonstrate that how principles of quantum key distribution can be integrated into a secure chat application using Qiskit. We simulated quantum key generation, and with Python and Tkinter, we created a user-friendly interface for securing communication. Although this simulation and it is not on real quantum communication system, but it successfully illustrates the core concepts behind the quantum cryptography. Secure message exchange. This was our main aim, that securing the messages which are exchanged between the users. The project also bridges the gap between the quantum theory and practical software development. Through this, we are implementing and simulating the quantum theory into practical application, right? So showing that quantum cryptography is just not a theoretical concept, but something we can simulate, visualize, and build upon today. Thank you for attention. I would be very happy to answer if any queries or questions are there. Feel free to drop a comment down there. I would be happy to answer all the questions and queries. Thank you for watching this video. I hope you got some insightful source or thing to learn from this thing, and stay connected.